All right, so this video, by the way, I think every single video that I've made, I've started by saying all right, and that's going to continue. So this video is going to be on flow orifices. They're used a lot in industry, and they could look a bit different depending on the type, but I'm going to go over the math of how they use change in pressure to calculate flow. And it all stems from the Bernoulli equation, which I still think is like the best mechanical engineering equation. If you know anything in mechanical engineering, you should know that equation. Cool. So as I mentioned, there's a couple different types of flow orifices. Like, they look different, but they all have the exact same math. So for example, the one that I'm gonna demo is like this. The bottom line doesn't look that great. Where you have flow, it's going from a large diameter to a small diameter. They can also look like this, where you have flow and it hits these walls and then it bounces and like goes through the middle. And you measure the pressure here and you measure the pressure here. But I'm not going to cover that one. Well, it's the same idea, but the math is easier if you use something like this. So yeah, the big idea is you have a pressure probe right there, P1. You have another pressure probe over here, P2. And based on the difference in these pressures, you can measure flow. Well, okay, first of all, why would the pressures be different? Big picture, mass is conserved, so the velocity here, V1, is less than V2, and V2 is over here. And that's because the Q, so the total flow at point 1 has to equal the total flow at point 2. But because let me draw that out, actually. Let me write out that equation. Q equals V1 A1, which also equals V2 A2. So Q is constant. But the velocity changes as a function of area. So on the left side, at point 1, we have a large area, so we're going to have a small velocity. But on the right side, at point 2, we have a small area, so we're going to have a large velocity. And from the Bernoulli, as a baseline, if velocity increases, pressure decreases. So that is conceptually how the Bernoulli equation is used. But let's actually do the math. Okay. So I'm going to write out the Bernoulli. And then loss term is V. I'm going to assume it's V2 squared over 2G. Technically, you could use the average of V1 and V2 as the velocity and the H loss, and that'll probably be slightly more accurate, but the math is easier and it's not that big of a deal conceptually. Yeah. All right, so typically the flow orifice, I don't know, it's less than a meter long or something. So we can assume that this loss is negligible. I'm going to spell it wrong, but probably wrong, but we can assume that loss is negligible. And for KL, there's only one loss component in this system, and that is just the orifice. So instead of KL, I'm just going to call it K. Cool. And then we start with an average height of the fluid of there, and we end with the same average height. Even if it's slightly different, it's also negligible. So we can cross out the heights. There's no pump in the system. There's no turbine in the system. I think that is it. So what do we do next? We rewrite what we have. Just times K. Okay. Cool. Next step, we use this equation to say you could solve either one. I'm gonna say V2 equals V1 times A1 over A2. Yep, and then we plug that in to here and to there. Okay. Very fun. V2 squared is V1 squared. Okay. Yep, that is it. Okay, now we move the velocity terms, so this term, and this term, to the left side, and the pressure terms, so those two, to the right side. So I'm going to do that. You know what? I'm gonna freaking copy it. Bruh. Okay. Equals P1 over, no, it would be P2 first. Okay. Now we can pull out V1 on the left side, and we can pull out the rho G on the right side. Okay. Now we can V1 squared. Yep. Okay, we can group these. Well, we can pull out the K. Well, we can pull out everything else except for the K. And I'm just going to say equals, and that assumes it equals a thing above it. Okay, almost done. This whole thing is just algebra. Okay, we get to cancel out those gravities. And we can multiply these 2's over to the other side. So we get v1 squared (1 minus a1 squared . Yep. And then we can divide this chunk over and take the square root. So we get v1 equals square root, and it's going to be the positive, not the negative. Yep. And then, okay. And our whole goal was to find Q, and that equals V1, A1. And we have V1. So now we just say A1 times this whole thing. Cool. And then, typically, when this is written out, it's grouped a bit better. I'll write it below. So you typically have part out front, which is cool. And the way you'll see it written is they call this part K, and they call this part root delta P. But that is literally it. Don't get these two K's confused. One of them is their Bernoulli loss, and the other one is, so this one's Bernoulli loss, and this one down here is the flow orifice K. So flow orifice K takes into account the Bernoulli loss K by default, as well as area ratios. And interestingly, you have to know the density of the fluid also. Interesting. But yeah, that makes sense, I guess. That's why there's temperature and pressure probes right where the flow orifice is, because that feeds into this equation, I guess. Cool, yeah, that makes sense. All right, but yeah, that's literally it. That's how flow orifices calculate flow rate. Cool beans.